Okay, sound testing. All right, hello, light testing. It looks good, I think. Hello. Oh my God, let me close the window. Oh. Alrighty. Ooh, what is going on today? Oh, hold on. I got. Alrighty. Okay. 3, 2, 1. Good morning. Hey. Hello, everyone. How's everyone doing? I am very happy to be here in the company of beautiful people like Arasto. Good morning. How are you doing? Debug. Welcome back. How are you doing? And and all the wonderful parametric campers that help me make this stream nicer, more entertaining, smarter, etc., etc. Now, what are we doing today? Let me pull up some files and some, because I have my script and I have the script and I have like like these files that I use to know what is going on and what am I doing every day, just to not get lost. And so this is working well. This is fine. And okay, so that's also good. Notes, all right. Okay, I need a couple minutes to get set up, it looks like. But as you probably know, we're going to continue recording the series intro, no, not intro, advanced development in Grasshopper, okay? Which is gonna take us a little bit of time. It's gonna take us. So remember how when I said that we were going to do a marathon, like when we did with Intro to Parametric Modeling, etc. I'm not sure that's going to be possible anymore because the semester has started. I teach a lot in the fall and I just don't have the time. So we're actually streaming today on Saturday just because it's the beginning of the semester and I'm extremely busy. So I think this September and probably October is going to be bumpy. Streams are going to be here and there whenever I have time. I just don't know what we're going to do. So just for the month of September and for the month of October, just try to be as checking social media and checking Discord and signing. So I forgot to say, we have, for those of you who might be new to the channel, good morning. My name is Jose Luis. I run this thing called Parametric Camp. We do live streams where we record tutorials on computational design, all things code, creativity, etc., etc. We're right now in the middle of recording a series called Advanced Development in Grasshopper, where I will hopefully teach you how to script inside of Grasshopper and how to create your own components and your own plugins. If you want to know when we go live, the best way to do that is to follow us on social media. We post on Twitter but mostly on Instagram. And during the week, we also have offline conversations in the Discord channel that I am posting on the server, on the chat right now. And we also have a Google Calendar that you can subscribe to. And whenever we go live, you will have a notification. You will have it over there. I posted a link to both things on the chat in case you want to be, and also probably the best way is to subscribe to the channel, to turn on notifications so that you get messages and emails whenever we go live and whenever we publish new videos. Because what we do is we go live, we stream, I record tutorials while I'm in conversation with fellow friends like Paras. I don't know if you have been here before, but you're more than welcome. Michael, it's good to see you. Hi from Arizona, was it, right? Andres, good morning to you too. ¿Cómo estás? I believe Andres is joining us from Monterrey, correct? In Mexico? Anyway, what was I saying? I lost track. Uh, I lost track. Yes. Anyway, okay, I lost track of what I was saying. Yeah, I may have had a little bit too much coffee this morning. I'm actually having an espresso in a teacup, so that I don't overdo it. Okay, yes. And so what are we doing? Yes, we record live streams and then we chop them, we edit them, and we turn them into videos that we publish on the channel. So what we're doing right now is we are recording a series, Advanced Development in Grasshopper, and we already had a set of videos that we did last week on Friday, where we recorded the introductory videos, and the playlist is already live. Arasto, who is right now on the chat, is helping me a lot to edit those videos and to make them accessible to all of you. Thank you very much, Arasto, for all the work and all your contributions to the channel. And today we're just gonna do a little bit more. So I believe last week we did Intro to Advanced Development, Why to Write Code in Grasshopper, Fundamentals of Scripting, the C# script component, and then we did a couple examples about simple components like arithmetic and blah, blah, blah. So I think today we're going to talk about what the Rhino Command is, how do we do scripting with geometry, and we're going to do an exercise with vectors, which, you know, it's one of my favorite topics in the world. And we're going to do advanced geometry scripting, which for this we need to take a look at what is a good example to do this, because I'm not sure how can we illustrate more idiosyncratic things in Rhino Command, like, you know, curves, VREPs, etc. So I'm going to need to think a little bit about this, I think. So I can either do that live here on the channel, or I can do that offline while I'm having lunch today. You know, lunch and geometry, you know, that sounds pretty appealing to me. All right, so I think in my series, sorry, the first thing we're going to do is we're going to open Rhino, because, you know, why not? Okay, and I'm going to dock this here, open Grasshopper, which just opened in the wrong window. I'm just going to put it here. And today we're talking, the first video we're going to record is what is Rhino Command. So for that, what I would like to do is, what I would like to do is I would like to record a video where I explain that in the previous videos we have done vanilla C#, which is just, you know, using numbers and strings, things that come with the core of C#. And what I would like to talk about now is how, in order to work with additional types, with all the geometry types, that's not part of the standard C# framework, but we need additional functionality, and that comes in the form of Rhino Command. And after I do that, I would like to take a look at the Rhino Command documentation. So I probably want to fire up some the Rhino Command. I probably want to fire up the Rhino Command documentation. This I will probably need to put a link on the video, correct? So let me remind myself of doing that here on my notes. What day is it today? It's fourth, okay? Hi, Pavel. Oh, Paras. All right, so good to see you again then. Adita, Adi. I like it. I like it too. So I need to probably write that in my notes. And then once I talk a little bit about Rhino Common and I go to geometry, I can probably talk about how there's a bunch of types, Basilia curves, B-reps, curves, meshes, blah, 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 points. And then there's structures, points, circles, boxes, cones, lines, etc. I would maybe want to talk about the difference between structures and classes. Is that what I want to do? Do I want to do that? And enumeration. So, okay. Maybe. Maybe I want to talk a little bit about that. I'm just going to expand all of this and then I can probably unspan it. And then after that, we are going to, I'm not going to code in this. I'm not going to code in this. I don't think I'm going to code in this video. Yes, so I'm just going to show Grasshopper. I'm going to show the parameters and I'm going to show booleans, blah, blah, blah. And then I'm going to talk about geometry. Where is this coming from? I may talk about that. And then in the next video, we will do a few examples using geometry types, okay? And I also want to point to the this one. I also want to point to this video here, Rhino Common and Rhino Common 2. And Rhino Common 2. I probably want to point to these two videos. Okay. And then in the next video, I discuss how to script with this. Okay, that sounds like a plan to me. Any questions, concerns, things you want to take a look at? Feel free to post them in the chat. Otherwise, we're about to start, I think. It's about time. All right, and this I cannot make any bigger, right? No. Should I bring any example from I'm going to bring an example. I'm going to bring a file from the previous example. So that's going to be files here, and the C# script component, and all right. And I'm going to open this, and all right. And I'm going to talk about this. All right. Okie dokie. And for this video, I don't need to make an introduction because I think the introduction is going to be just what it is, because we're not really going to write anything. Okay. Thank you, Michael. I'm very happy they helped. Okie dokie. So, all right. So let's get started then. Okay. Ooh, the battery is not great. So if the sound goes away, can you please flash me on the chat screen? Because the battery is about to die. Hi, this is Jose Luis here at Parametric Camp, and welcome to another video in this series Advanced Development for Grasshopper. In this video, I would like to talk a little bit about this thing called Rhino Command, which is the geometry kernel that is fueling all the geometrical power that we're going to harness when scripting and when developing our own components inside of the Grasshopper and Rhino environment. All right? And why is that? Well, if you think about the examples that we have done previously in this series, you are probably acquainted already with the idea of the C# scripting component as a place where you can write your own C# programs and they can be executed in relation to the Grasshopper environment. And the programs that we have done so far look something like this. We can work with double numbers, we can operate with strings, we can do basic arithmetic, and all of that is great. And it's great because it's part of what the vanilla C# framework allows you to do. So C# is a programming language that has these primitive data types, numbers, strings, booleans, things that are common to every single place where you can write C# code. However, the problem is that C# itself, as a programming language, was not designed for doing geometrical manipulations of any kind. And therefore, C# itself, as a programming language, comes with no capabilities for doing any kind of geometrical operations whatsoever. The most fundamental types available in C# are numbers, booleans, strings, and a little more than that, but there's no vectors, there's no points, there's nothing like that. So where does all that goodness come from? Well, if you take a look at Grasshopper, and if we go back to the primitive step, you can see that there's this category called primitives, which has these four types at the beginning: Boolean, number, integer, and text, which kind of correspond with the primitives that are available in C#. Boolean, integers, doubles or float numbers, and strings. They just have slightly different names. So there is a very close one-to-one correspondence between native C# types and the way Grasshopper treats them. But all of this, the rest, colors, domain, domain square, and especially all the types that are available as part of the geometry category, points, vectors, circles, boxes, meshes, surfaces, B-reps, curves, you name it, all of this, again, they don't come with C# out of the box. If we want to be able to use curves, points, and vectors when writing computer code, we need to have something else added on top of our baseline C# programming language that gives us all of those additional capacities. Think of it as additional features, or just like in Grasshopper, we can have plugins that give us extra functionality. Programming languages like C# can also have plugins that give them extra functionality. Those plugins are typically called libraries, code libraries. And in terms of C#, they come in the form of DLL files that we can load and that give us all this additional functionality. In the Rhino and Grasshopper environment, that functionality, that additional functionality and all the geometry types and all the geometry goodness comes from this additional library of code that is available in this environment, and that is called Rhino Command. Rhino Command is a really powerful library that comes with a lot of tools for drawing things in the screen in Rhino, manipulating buttons, and then things that have to do with Rhino as a software. But on top of it, they come with a specific section for geometry that has all the goodness that we will be interested in this series. So where is Rhino Command, or where can I learn more about Rhino Command? Well, first of all, the developers of Rhino, so McNeil, gives us a documentation that allows us to parse through what is available in Rhino Command. So for example, if you go to this link, which I will post somewhere on the description, or maybe it's going to show up as a card here over in the video. If we go to this link, you can see that this thing called the Rhinocoma API, the application programming interface, is basically a documentation file that tells us everything that is available in Rhinocoma. How this gets loaded and why this is available as part of Rhino, whatever, this is a bit more of an advanced topic, but we will see some details about that in further videos down the road. But for the time being, I'm more interested in understanding what Rhinocoma is and what has available, and giving you the tools to further do research on how to learn about Rhinocoma. So Rhino the library has a lot of namespaces, which is basically folders, if you will, or categories where certain functionality, classes, functions, etc. are distributed. For the case of this course, we will be mostly interested in the rhino.geometry namespace, which will be the namespace that will have all the classes for geometry types that we will be interested. I'm going to fold this to 3 categories, and I'm going to show how the geometry namespace basically has 3 categories: enums, structures, and classes. In previous videos or in my Learning C# series, I have talked about the differences between classes and structures. They're really, really similar. The only difference is that there's a little bit of how values are passed by reference, etc., that differs between them. But in very, very general terms, with a lot of exceptions, you can think of structures as useful for representing simpler data types, and you can think of classes as useful for representing more complex data types. All right? We will talk a little bit of how they work differently in a second. So if I unfold structures, for example, you can see that there is a lot of types that are available to me, like for example, arc, circle, there's cone, there's an ellipse, there's a plane, which we will use extensively here. There's point 3D, which stands for point with 3 doubles, so a lot of precision, as opposed to point 3F, which stands for point with 3 floats, which has less precision. We have quaternions, scary quaternions. We have vector 3D, also 3 doubles, and vector 2F, vector 3F, 3 floats, all right? And we will be using many of these a lot. Why these are structs? Well, again, that doesn't really matter for us a lot right now. It's just because they're simpler data types. Points are very simple because they can be represented with 3 numbers. Same goes for vectors. Circles are also pretty straightforward, a center and radius. Planes are basically a center and 2 axes, so they're pretty straightforward numerical types. And because we also typically work with a lot of them together, that's why we typically represent them with structures. Anyway, this is not our choice. This is how the library has been designed. But I will talk about more of that in a second. And then we also have classes. Classes represent more complex geometry types. For example, you can see here that we have Basilia curves, we have B-reps, and B-reps are really complex. They have a lot of information, etc. We have curves generically. We have the geometry base, which is the base type that all geometry objects inherit from. We have a lot of like mass properties. We have meshes, and meshes are like really complex structures as well. We have nerve surfaces, we have polycurves, we have polylines, I believe is part of it. I think that there's a lot of them. So why is this important? This is important. Being able to have access to this documentation and to understand how it works is important because it will give us the entry point to understanding what is the kind of things that we can do and the kind of geometry that we can model inside of Rhino. So for example, if I go to the point 3D struct, and then I open it, you can see that it tells me, well, it represents coordinates in 3-dimensional space. The constructors are, I can create it in 5 different ways from other points or from 3 coordinates. And if I want to know more, I can just click on it and see, you see, this is a constructor that initializes a new point defining X, Y, and Z coordinates. This is the constructor, and this is the 3 inputs. And sometimes you actually get tiny examples, for example, in C#, in Visual Basic, as we saw before, or even in Python sometimes, especially for the simpler classes. Now, for example, also inside of Point3D, I can see that Point3D has a set of properties. So for example, we can get the X, Y, Z values of a point. We can say whether if it's valid or not. Or for example, we can do operations. So points, the Point3D struct has methods. Like for example, I can add 2 points together. I can compare points. I can calculate the distance of one point to another. I can multiply 2 points together. I can multiply a point by a scalar, etc., etc. All right. This is very important, and then we can always click on each one of them and see like, oh, I can add 2 points together, and this happens to be a static method, which we will take a look at very soon what that means. Or for example, I can go to the vector tab and I can say vector 3D. I can create vector 3D from another point or from another vector or for 3 components, and I can find the length of the component. I can find the X, Y, and Z coordinates. I can find whether if it's a zero vector, whether if it's a unit vector. Those are properties of the vector struct, right? I can also add 2 vectors. I can also check if 2 vectors are orthogonal, if they form 90 degrees between them. I can compare a vector to the other. I can calculate the cross product of 2 vectors. I can check whether if 2 vectors are parallel, etc. So I can see all the information. I can unitize vectors, and we will be using this a lot in this series. And I can, so there's a lot of information that I can learn from taking a look at this documentation. Similarly, for classes, I can take a look at more complex classes and see what functionality is available for them. So for example, if I were to take a look at the nerves curve, where is the nerves curves? Nerves curve. I can see that the nerves curve class has a lot of information. So for example, I can create a nerves curve from another one. I can create from some control points. Nerves curves, I can take the degree of the curve. I can take the domain of the curve. I can ask whether if it's closed. And you can see that if I click here, it will tell me that the result of this is a Boolean, right? So I can read that from the documentation. Whether if it's periodic, which is the same as whether if it's closed. And then I can fetch the point at the beginning, and then you can see that the point start property gives me a Point3D object in return. We will see examples of all of this very soon, all right? I can find the tangent at the beginning or the end, or I can use methods, I can use functionality to find additional properties. So for example, I can find what is the closest point to this particular nerves curve, and I can give it a reference point, and I can use a double to express the tolerance, I believe, or the maximum distance, right? If I don't know what this double property is, I can just click and see. You can see the double is the parameter of the local closest point, all right? And I can see that it's the way it works is that it needs an out parameter, which is also something that we will see very soon, as soon as we start taking a look at how to use all these methods, all right? For example, I can find a point at a particular point. So for example, I can say, where is this? I can find a point at a particular parameter along the curve. I can find a point at a particular length, which remember is different from the parameter of a nerves curve. And there's many other things that I can do. All right. So what my point here is that what I would like you to understand is that there is this core geometry kernel that is called the Rhinocoma API that contains this particular section called the Rhino geometry, which has all the goodies and all the nice geometry stuff that we will be using consistently for modeling in 3 dimensions and for writing our own scripts and our own plugins. All right. And the way to learn more about how things work and what possibilities do we have is by checking the documentation, finding the types that we're interested in, I want to create a Basilia curve. So let me just Google Basilia curves. Oh, interesting. So there's a particular class. It's called the Basilia curve. I can create from a bunch of points. I have the dimension, whether if it's valid. I have like a set of other properties. So I can learn a lot from reading this documentation. So this documentation will be the cornerstone for our learning of how to interpret and how to use the classes that exist in Rhinocoma. Okay. Before we go, I would like to point you to additional resources if you want to learn more about learning and interpreting the Rhino Common documentation. We're going to do that. We're going to do this in a few videos down the road, but in my series of in the lectures of my course at Harvard University, I have there's a lot of lectures about geometry data types, but there are two specific sections, two specific lectures where I talk extensively about Rhino Common, what it means, and how to read the types and how to read the documentation. So if you want to learn more about that, you're more than welcome to check these two videos, to which I will also link in the description of this video. All right? Beautiful. So with that, let's actually now try to use geometry types inside of Grasshopper. So in the next video, I'm going to start creating C# script components that instead of just using numbers and strings, are going to start using geometry types and spitting out three-dimensional objects. Okay? That's going to be super exciting. Join me on the next video. And in the meantime, if you like what you're seeing so far, perhaps consider liking this video or subscribing to the channel, or even hitting the bell icon and turning on notifications to know when we go live. Okay? All right. See you in the next video where we're going to do some scripting with three-dimensional geometry. Alrighty. How was that? Can you folks give me thumbs up, thumbs down, thumbs horizontal? Whatever you think. Whatever you think. Was this clear? Was it too superficial? I think it's enough to start. We're going to do some examples later, but I didn't really want to get too deep into it. Hey, Albert, good to see you. And yeah, I didn't want to get too deep into it at this point. All right. Okay. So that's one video. What is next? Scripting with geometry. Ooh. Beautiful. Hey, Fernando, good to see you. It's been a while. How you doing? Okay. So scripting with geometry. So what we're going to do is we're going to show, I have my notes here. I have the notes that we did together in this one live stream where we designed the curriculum of this video. That was actually quite lovely. Can you do everything in Rhino Common in vanilla Grasshopper? Whew, that's a really good question. I think I would say no. I would say no because I would say that a lot of Grasshopper components are very simple interfaces, or if you will, just a facade behind very straightforward Rhino Common methods. Okay, so that's one thing. So when you create a point in vanilla Grasshopper, you're basically calling the create point function in Rhino Common. So there's a very clear one-to-one correspondence. The other thing is like many Grasshopper components actually perform much additional work than the Rhino Common simple methods because they do additional checks and there is additional functionality in Grasshopper, in vanilla Grasshopper, that is just not part of the plain. It's just not part of the plain. I'm gonna say this. It's not part of the plain set of functionality that comes with Rhinocoma. That's the second thing. And the third thing is that I believe there's a lot of stuff in Rhino Common that is not available in Grasshopper, in plain Grasshopper. And that is because It's just things that are not or very useful or very common or that don't match well the nature of Grasshopper. Okay, there are not that many of those, but yeah, that's how it works. But what it is true, Albert, is that anything that is available in Rhino Common will be available to you here in the C# script component. So if you drop a C# script component and you click here you will have access to the full Rhino Common set. All right. So if there's something that you're missing in vanilla Grasshopper, you could create your own C# script component and access that functionality from the component. All right. That's one thing. Michael, yeah, it's very useful. It's really good to have in mind. Let me actually remind myself that I need to add links to stuff. Add links cards to Rhino Common Docs plus GSD lectures. Okay. All right. The automatic screen behind you sometimes flickers on the corners when you stand. Oh, can we try that? Wait. Let me try to see if I can reproduce that bug. All right, so if I stand, if I do this, okay, that thing, right? Is that what you mean, Arasto? Okay, yes, so this is because I have a post-it note. Okay, let me try to fix that. All right, hold on. I'm going to do some. All right, so, and we're going to use high tech for this. All right, we're going to use high tech for this. Oh, thanks for letting me know. Okay, so high tech. I'm gonna put some tape. I have a post-it note on top of the webcam that is preventing the glare of the focus light from, because if I do this, you see glare. But if I have the post-it note, there's less glare. So what I'm going to try to do is a really shitty fix, which is all right. How about that? All right, looks like it works. And it looks like the glare is not affected. All right, so that should be good. All right. All right, we're good. Thank you for pointing that out, Arasto. Okay, what else do we have? So all you have in Rhino is in Rhino Common. You mean Rhino commands? Like when you type stuff in Rhino, like create line, rotate things, whatever. Those commands are based on Rhino Common functionality. Yes. And all the geometric operations are part of the Rhino Common set of tools. Yes. Now, when it comes to commands, there's also, it's like Grasshopper components, it's not always a one-to-one exact correspondence, but for the most part, yes. Is it possible to create an executable file that loads code created using Rhino Common without the need of Rhino and Grasshopper running? Yes, that is a possibility, because there is a way to find the file, and we will see about that in future videos, Fernando. There's a file, literally it's called rhinocommon.dll, that is in Rhino. So in your Rhino folder in the root, you can find rhinocommon.dll, and that's the file that contains all the geometry goodness. So if you take that file and you take it and you write your own software and you use that file, and you use that file to load into your software and to do something, then you can access all that functionality. The caveat is that the license, the Rhino license, doesn't let you do that legally. So you can technically do this, but you should not do that because the Rhino license doesn't let you do that. All right. Yeah, like a standalone application. Exactly. Yes. Now, as Victor is pointing out, what Rhino gives you as an option, as an alternative to do, is something that is called Rhino Compute. Rhino Compute is a service that allows you to ask for a particular geometrical operation on a cloud service and get a response with the result of that geometric operation. Imagine a Rhino common that lives on the cloud, or, well, I mean, you can actually deploy it locally on your system, but a Rhino common that lives on the cloud and that you can talk to and get information back and forth using network communication. All right. So that's kind of what, that's also an alternative, and that's a legal one. That's one that you can subscribe to. You have to pay a little bit for the service, etc., but it's a solution to being able to provide the Rhino Common functionality as a service. Okay. By the way, hi Victor, good to see you too. Arasto. So you can actually use the vrep and the surface stuff if you use the Rhino common file that comes with Rhino. But if you use the versions, like what is the name of the file? Let me find that out. There's this other project, Rhino 3DM. No, Rhino 3DM NuGet. So this, I forget whether if, because this one was deprecated, no? So there's this version. This is the file that you can use. Rhino 3DM is the Rhino Common library that you can use to load 3DM files and to do simple geometrical operations. But this is the one that does not have the surfaces and the VREPs and the intersection, etc., etc. All right. Could you teach us an example like that? I could, but it's not on the curriculum right now. But it's a very good point, Fernando. So I may think about how to insert that in the curriculum. Or I may think of how to do a geometry jam or something like that. A geometry jam specifically on that. Okay, so, but that's a very good point. Cool. So, okay, so geometry types. All right. Scripting with geometry. Well, I do not want to close the documentation. So I would like to keep it somewhere here, because I may go back to this as we are recording the tutorial. Okay, so I'm gonna shut this down. I don't need this. We're going to save this as 3.2. Is that what we're doing? How is life otherwise? How are you folks doing? Just doing a little bit of small talk while I set myself up. Yes, Andres. So much of the functionality that lives in Rhino Common, the C# library, is actually pinging an underlying C++ library that is the one that actually performs many of these operations. Yes, that is true. It's just that when it gets compiled together into a C# project that then we can use. So we don't need the underline headers and the C++ or, we don't need any of that. Okay, so simple example, scripting with geometry. So what are we going to do? We're going to see examples of how to create a point, vector, a line. Okay. So we're going to create a component that creates a point, a component that decomposes a point, a component that creates a line between 2 points, and then I'm going to see if line has, and we're going to find a point at T on a line, then a vector from 2 points. We can do that as well. We could do that as well. Create a plane from input components. Discuss play. Okay. And then in the actual exercise, we're going to do some vector algebra. I think that's going to be a good video here. I want to talk about vectors and points being structs and how you can copy them. I wonder if I should make a special video for that. I may just do a video somewhere down the road in the advanced part. Okay. I may just add that. Where can I add that? Yeah, that's going to be its own video. Maybe just do it here. Or maybe a little bit farther down, because I want to talk about data component messages, data component, persistent data, continuous executions. I may just do it at the very beginning, right here. So, so struct types versus class types. Example of copying, unitizing a vector. I know what that means. It's in my head. So yeah, I'm not sure if that's the best place to put it, but oh well. That can be the first place we. Okay. So all right. So back on track. So let's do some points, some vectors, some lines, and we're going to do this. How are we going to do this? We're going to do this. We're going to do this. How are we going to do this? I'm going to do this. Yeah, I'm going to record the introduction at the end, and then I'm going to start right away doing it. And that's going to be, yeah, I'm going to start doing it right away. All right, so I'm going to start doing it. Sorry, I'm going to start doing it, and then I will record the introduction later. Okay. Let's get started. We're going to start by probably the simplest component that I can think of geometry-wise, which is going to be creating a point in 3 dimensions, okay? So what I'm going to do is I'm going to drop my C# script component, and then I am going to add an additional input here, and very conveniently they're already named X, Y, and Z, which it feels like the kind of name that I would give to the inputs of a component that I want to create, taken as inputs 3 numbers. All right. So the next thing that I'm going to do is I always need to remember that I need to type the inputs, right? So I'm going to say the type of X needs to be a double because it's going to be a number. The type of Y is going to be a double, and the type of Z is also going to be a double. All right. So now I have a component that can take 3 numbers. Let me actually give it 3 numbers. So for example, actually, I think I want decimal parts, so I'm going to double click and say 10.000, and then I'm going to copy and paste this 3 times and give it some values here. And my OCD doesn't let me keep those that way, so now I have the inputs. All right, I'm going to rename the output. I'm going to call it P because it feels like it's a point, right? And then I'm going to double click here, and I can see that my inputs look correct. So I have X, Y, Z as doubles, and the object, the output, is P. All right. So as we typically do, I'm going to write here my algorithm, and then I'm going to output here the outputs. All right. What is my algorithm going to be? Well, I just want to create a point from 3 numbers. So that's going to be super easy. And if you remember, we're going to go back to Rhino, the documentation. We're going to scroll all the way down to structs to find all the types of points that I can create. The most common one is going to be point 3D, not for 3 dimensions, but as I explained before, for 3 double precision point values. So 3 numbers with a lot of decimal precision, right? So, and you can see that I have the constructors here. So I'm just going to go ahead and do it. So I'm going to define a new variable of the type point 3D. So I'm going to type point 3D P, and that's going to be a new object. And you can see how IntelliSense is already giving me a suggestion. Oh, I think you want to create a point 3D. So, and you can see that here I get, oops, all right. So here I have a suggestion and some helper text. So I'm going to hit enter. I'm going to open, and you can see that as I'm already getting suggestions that are coming from Rhino Command. You can see that the constructor here has 5 overloads. You can see the 1 of 5 note here. And if I press the arrow down, you can see how it's telling me all the different ways I can create a point 3D. From 3 doubles, like here, from a vector, which means probably copying the XYZ from that vector, from a point 3F point, so another point with less precision, from another 3D point, a point with the same positions as a copy, or from a point 4D. Can we create points in 4 dimensions? All right. So I'm just going to stick to XYZ, and I'm going to use X, Y, and Z, which just happen to be the names of the 3 inputs that I have here in my component. All right. So this component, this variable P, already has an object of the type point3D. And for the output, I can say uppercase P. Remember that C# is case sensitive. So uppercase and lowercase make a difference. So the output P, the output of the component, is going to be equal to the lowercase p variable that I design in my algorithm. If I click play, you can see that everything works fine. All right. And that here I now have a point in 3-dimensional space. I can make sure that this is the point that I just created here by putting a panel, and then you can see that now as I move my sliders, I have this point in 3D. So basically what I have done is I have just recreated the construct point component. In the construct point, the code that is running inside is exactly identical to what I just wrote here. Okay, cool. So, well, if we do the construct point, can we deconstruct a point? Can we take a point and figure out the x, y, z coordinates of that point? Of course we can. It's going to be super simple. So let's do that. But before, I'm going to write here construct point 3D, and I'm going to use the paint bucket so that I have here my annotation. So the next thing I'm going to do is I'm going to drop a C# component, and this one I'm going to do the opposite. So what I want is to take a point. So I'm going to zoom in, I'm going to remove inputs, I'm going to rename this to uppercase P, okay? And then remember, I have to type it. So in this case, the input is not going to be a number anymore. So now here we're coming to an interesting part. The input is not going to be a number or a primitive type. It's going to be a complex type, or it's going to be one of those Rhino-Command types that we have in the geometry kernel. And you can see that also very conveniently, oh, my head is on the way. You can see that very conveniently, these ones are the simpler types that I described before, the structs, okay? Whereas one totally in the middle, right? Whereas these ones are the more complex ones. So that would be, I'm making it worse. Okay, hold on. That would be, all right. So that's going to be line, circle. Actually, those are also structs. So I'm not sure that I'm doing a good case here. Curve, surface, B-reps, whatever meshes, those are the more complex data types, if you will. Okay. So what are we going to do now? We need to make sure that this was 0.3D. Okay, so we're going to set that up. And the outputs are going to be the XYZ coordinates. So we need to change this to 3 outputs. This is going to be uppercase X, uppercase Y, and uppercase Z. And I'm choosing uppercase just because to keep symmetry with the vanilla Grasshopper components. And then I'm going to plug a few panels right here. So I'm going to plug a panel here, another, and then I'm going to plug another panel here, X, Y, and Z. All right. Okay, so now if I plug this point, you can see that nothing happens, obviously, because this component has absolutely no code inside of it. So we need to fill in the code, but at least the structure is already in place. You can see that the argument of the function P is now of the type 0.3D, and we have 3 outputs, X, Y, and Z. So let's just do this. And for this one, I'm actually not going to write anything as an algorithm because we can just simply output all this information right away. So for example, I can say X is going to be equal to whatever I do this. So, oops. Sorry, I need to change the batteries in the microphone. Testing, testing. All right. Okay, so let's continue. Oh, sorry for that. I had to change the batteries in the microphone. So what you can see is that because the object P, the variable P, is of the type 0.3D, when I hit the dot accessor, what I can see is that now the autocomplete is telling me, is popping a bunch of the methods and the properties that are available inside of 0.3D objects. So as I was saying before, I can compare points, I can calculate the distance, I can interpolate points, which is the same thing as you would find here. You see, you can see the distance too, you can see interpolation, right? You can also see that we have the X, Y, and Z properties. Those will be here. So you can see that if I scroll down, I have the X, Y, and Z properties, and it just gives me a helper text to understand what's going on. So it turns out that this is very helpful. This autocomplete is very helpful to try to see what is inside particular geometry types. So X is going to be the property that tells me the X coordinate of any particular point. So I want to output in the X output, so that's this one. What I want to output is the value of the X property that lives inside of the point object P. All right? And similarly, I'm just going to do Py, and C is going to be P dot C. Okay? I'm going to press this, and as I do, you can see that now this component is outputting in the output the 3 numerical values for this point. And if I change the input values, you can see that these inputs are changing. All right? And that the values are updating correspondingly. All right, so now I have just created the deconstruct point that lives inside of Rhino, inside of vanilla Grasshopper. Okay, beautiful. So we have construct and we have deconstruct. What else? All right, so that's great. What is the next thing that we can probably implement as an example here? All right, I see a lot of activity in the chat. There's a problem, but if you want to use compressor, it will give you an error. If you need to load Rhino Commands to Rhino.s for the full function, which means you can use it for plugin development. Standalone full functionality is not possible. Yep. And then it comes to the answer, but they've written about this. The error would look something like this. Oh, can I actually point? Because I had that conversation very recently. I wonder. Right. What is the forum? Rhino 3D forum. McNeil. Yeah. I was literally. Okay. Yes. So I'm going to post here a link where I had a conversation very recently with Steve and with Dale about that particular topic. Yes. Yeah. Technically speaking, Rhino Common, the DLL is not meant to be used outside of Rhino Common. It's meant to be used only by things that live inside of the Rhino Common environment. Okay. I have a few things going on, sorry. Okay. Oh, yes. So, sorry, I need to send a text message. It's urgent. Just give me a second. Okay. Yeah. Okay, beautiful. So what are we doing? What is the next thing that we're doing? We are doing, oh, by the way, we're doing a double live stream today. So I'm going to be streaming at 2 p.m. my time as well. We're going to decompose point. We're going to create a line between 2 points, okay? So, all right, so let's do that. How about creating a line between 2 points now? I mean, that sounds like a next straightforward step. So what is the original component for this? The original component, I think it looks something like this. Line between points A and B. So we're going to try to mimic this, okay? And we're also going to do it already from our point here. So we have, I'm going to construct 2 different points, okay? So this is going to be 1 point and this is going to be the other point, all right? And they are separate in 3-dimensional space. And I'm going to turn this off. And what I'm going to do is I'm going to try to create a line between these 2 points. So I'm going to create a component that creates lines between 2 points. I'm going to say the input needs to be called A. I'm going to do uppercase A. The other input is going to be called uppercase B. And remember, I need to type them. This is very important. I forget all the time. Okay. So I'm going to right click on A, type hint, and I'm going to choose line. No, I'm going to choose point 3D as an input. And the other input is also going to be a point 3D object. And the output, I'm going to rename it as L. And remember, outputs don't need to be typed because they are generic types for design reasons that we don't really need to get to in here. Okay, beautiful. So I have the component that generates a line between 2 points. So now let's write some code in here. So also super straightforward. Algorithm and then outputs. So I'm going to create an object of the type line. How do I know that that's the type that is called line? Because if I scroll in the documentation, you can see that here there's a thing called line, and that I can create a line from 2 points, from a point in a vector, from a point in a vector in a double, from 6 numbers. I'm going to see that, and I can see that lines have the from point, the to point, the coordinates of each one of them. You can find the closest point. You can flip the line. There's a lot of stuff we can do. We're going to do a couple examples here. So, for example, let's say I'm going to call the object lowercase line. And I'm going to say this is going to be a new object of the type line. And as I open parentheses, the autocomplete gives me suggestions. 2 points gives me a point and a span, point, direction, and length, or the 6 coordinates of the 2 points at the ends. In this case, I'm going to choose point from and point to, which are going to be point A, that is coming from the input, and point B, that is also coming from the input. And then in the outputs, uppercase L is going to be equal to that line variable that I just created. Very simple, very clean, very straightforward. I'm going to do that. And right now, I'm going to plug a panel here. Oh, wow, what just happened? Whoopsies. Oh, I think I copy-pasted a lot of stuff. Sorry. I'm going to copy-paste this. You can see that there's an invalid line because nothing is happening. And this, as I plug in the 2 points, you can see that I now have a line in 3 dimensions that if I change any of the original inputs, the line changes. So we have a line object. Woohoo! Line object, paint bucket. We have our own implementation of a line object. All right. Something else that could be interesting is, can we find a point along the line? How does that sound? Let's do that, because that's going to be more interesting, because it's not just creating an object, it's creating an object using somebody else's function. All right. So I believe that is done here in vanilla Grasshopper with the point on curve, which is a little esoteric because it has this UI with a slider, whatever. We're going to do it a simpler way. We're going to create a C# script component that is going to take a line as an input. So that's going to be uppercase L and just uppercase because that's how vanilla Grasshopper does it. And the type is going to be line. All right. And now the other input is going to be how far along the line we're going to get that point from. But we're not going to use Euclidean length. So we're not going to use real length. We're going to use parameter. All right. And as you know, parameter is that property that tells us how far we are along a curve in relative terms. All right. So lines, for example, always start with a parameter 0 and always end in a parameter 1, no matter how long or how short they are in 3D space. So it's the proportional length along the line, if you will. So we're going to call that lowercase t. That is a very common way of representing the parameter of a curve. And this is going to be a number. So I'm going to choose double because it needs to be a number from 0 to 1. And then the output here is going to be p, which is going to be the point along that line. Let me choose here a slider that is going to be, for example, at 1.0, okay? And I'm going to plug that in here, and I'm going to plug this line as well. And then the output is going to be p, which I need to encode, correct? So I'm going to double click here, and now I have my inputs, the line L, parameter T, and the point P. So, algorithm and output. Okay, so how can we do this? Well, there's two ways we can do this. First, we can do it the manual way. So we can find the XYZ coordinates of the points of the line. We can calculate their distance between them. We can factor those distances by the parameter, and then we can recreate a new point in 3D. So that would be the manual way. And I believe I actually have a geometry gem somewhere where I did that. If that's the case, it will be popping somewhere here on the as a card, or it will be in the description of this video. But since this is a little bit more about learning Rhino Command, so let's see if there's any functionality in Rhino Command that we can access to be able to figure that problem out. So what would be the way to do this? Well, we could use the intelligent suggestions to see if there's anything like that, or we can take a look at documentation, which is always probably a better approach, I would say. So if we go to the line structure and we look at the methods, so at the functions that are inside line objects, we can see that there is one here called point at, which if I click, it tells me that it evaluates the line at the specified parameter. All right. And then that the return type is going to be a point 3D object. This means that if I tell the line that I want to point at a particular parameter, it will return that point. So very nicely, I have some examples here that we could look at, etc. But I'm just going to do it myself. So what are we going to do? The algorithm is going to be point 3D PT is going to be equal to a point that I'm going to generate from the line. So I'm going to say L, which is the line object that I'm reading from the input, dot, and then I'm going to start scrolling all the methods, all the functionality. You can see this is everything that we have seen in the documentation. Here I have point at, which evaluates the line at a specified parameter. I point out, I open parentheses, it asks me for the parameter, so lowercase t, and the fact that this in the documentation is lowercase t, and the fact that this in the input is lowercase t as well, is just a coincidence, but they don't have to have the same matching name, okay? And then the output p is going to be equal to pt. Let's see if this works. If this works, would mean that a point at parameter 0 would be all the way at the beginning, and a point at parameter 1 would be all the way at the end, and a point at parameter 0.5 would be right at the center of the line. And what that means also is that if I modify any of the inputs, everything should be parametrically bound, correct? Beautiful. So it looks like we have been able to create a line, a point at line. All right. So now with this, and actually, let me show you a trick. Lines have a domain that goes from 0 to 1, but that doesn't mean that we can only find points from 0 to 1. So if I actually change the domain of this from -5 to +5, we can also just find a point that extends over the line outside the 0, 1 domain of that line. It just does so proportionally to the length of the line. Correct? Beautiful. This is looking really cool. What is the next thing we're going to do? I think it's time for vectors, isn't it? Okay. Add links cards to the point at line geometry. Okay. And have I also said anything about any other thing that I want to Oh, Arasto, thanks for sharing that link on the live channel. Yeah. Okay. Is there any Any other thing that I don't remember. Okay, so maybe just not. Okay, so what's next? Vector from 2 points. Vector from 3 points. I haven't Arasto yet. I haven't tinkered with Rhino inside, no. It's on my to-do list. And as soon as I play a little bit with it and I make something, we will probably record a few tutorials on that as well. Okay, so I'm getting a headache today. Hope it doesn't get bad. I'm going to take a bio break. I will be and drink some water. I'll be right back. Just give me 1 minute, okay? I'll be right back. Ooh. Okay, we are back. Ah. What are we doing now? Vectors. We're doing vectors. Andres, in the last example, if the full domain is 0 to 1, right? We do not need to. No. So the way nurse geometry works, or maybe that's what I wanted to link. The way nurse geometry works is that lines are basically curves of degree 1, and they're always guaranteed to have a domain from 0 to 1, at least in Rhino. Okay? Curves can have a domain of whatever to whatever, and you're almost never going to get a curve from domain 0 to 1, so you have to reparameterize them, which basically means just changing their domain. That's a good thing. I'm going to write it at the examples. Divide a curve into points. Reparameterize a curve. So that can be interesting. We will do that as an example farther down the road. Okay. what else do we have? We're doing vectors. So we're going to point, create a line to point at the T on a line. Yeah. Vector from 2 points and create a plane from input components. All right. Let's do it. So we're going to do, for example, we're going to do the simple vector from 3 components. And I mean, you're going to see that that is extremely, I'm actually going to copy the construct point and I'm going to turn this into construct vector because I'm going to use the same XYZ inputs. The output is going to be V in this case. And what I'm going to do here is that you're going to see that I'm going to remove the algorithm here and the algorithm here. And then what I'm going to do is I'm going to create a vector 3D object called lowercase v. And that's going to be a new vector 3D from XYZ components. So X, Y, and Z. And then v is going to be equal, the output is going to be equal to that variable lowercase v that we just generated. As I do that, you can see that now I have this vector and you can see that the output actually is such a vector, okay? And if we actually want to visualize this, we can use the vector display component to just say, can I see this vector on, can I just anchor it at the center? And then you can see that this would be the vector that I just created, correct? However, this is a little boring. So how about we actually create a vector from 2 points, just like we have created a line from those 2 points. So let me show you a couple of tricks here. So I'm going to create a C# script component, and this is going to be, input is going to be A, the other input is going to be B, and I'm going to call this vector 2pt, and the bucket here, and then the output is going to be V, uppercase V. All right. Remember that I have to type the inputs. So this A is going to be of the type point3D, and this B is going to be of the type point3D. Now I have the 2 points that I have created here. I'm going to plug them over, and oopsies, I'm going to make a little bit of room for myself here, and I'm going to plug here a panel. So I have the 2 points coming in, and I want to create a vector between them. So there's a couple ways we can do this here. So I'm going to write the algorithm, and I'm going to output the outputs here. There's a couple ways that I can do this. So the manual way would be to say, I'm going to take the coordinates of A, I'm going to take the coordinates of B, I'm going to subtract them, so the x coordinate of B minus the coordinate of A, to find the difference between them, and then use those coordinates to create a vector between them. All right. So that would be the manual way. But we're trying to come up with more Rhino-Common ways of doing this. This is what I'm trying to teach you here. So I'm going to teach you, for example, a first way could be using some of the properties, or some of the, I believe the constructor has the possibility of doing this for you. So for example, I can say new vector 3D, but instead of XYZ now, let me see if I can create it from 2 points. Well, it turns out that there's no option to create it from 2 points. But because I know that geometrically, a vector between 2 points is basically the subtraction of the coordinates of B minus the coordinates of A, I could do it manually, as I said before. I could say the difference between E is Bx minus Ax, and I could do that for dy, dz, and create a new vector with these components. But instead, Rhino Common actually gives me a way to operate with components with points directly. So for example, what I could do is I can, hold on, give me a second. I don't know what I'm saying with here. Can I do this? Is there a static method? There isn't. Sorry, because I know that the meaning of creating a vector between 2 points is the difference between the coordinates. Rhino Command actually gives me a shortcut to making that happen. So it turns out that even though A and B are 0.3D types, they're not numbers, what I can do is I can actually operate with them. So it turns out that in this case, the expression B as a point minus A as a point is a valid operation because Rhino Common has this thing called operator overloads, which means that it gives me options to define what happens when I subtract two points together. And it turns out that the result of this is a vector that goes from A to B because of the geometric meaning of this operation. With this, what I can do is I can now say that the output V is equal to that new variable that we just created. I'm going to say Rhino Command operator overloads here. All right, let's see if that is true. I create a vector between these 2 points, but let me visualize it to make sure that it's correct. So I'm going to visualize the vector and I'm going to visualize it from the first point. And you can see that indeed this vector is going from A to B. And if I modify any of the points, you can see that indeed the relation stays correct. Beautiful. So how nice is this? This idea, the idea that I can subtract two things that are not numbers, again, is a special functionality that Rhino Command gives us, and it's called operator overloads. All right. Wonderful. And last but not least, perhaps we want to create a plane out of the origin point and two vectors. So let's just do that right away. So I'm going to construct a point here. I'm going to construct a point. I'm going to construct two vectors. I'm going to construct two vectors here. Okay, I'm going to delete all this stuff. And here I'm going to create, so for example, this is the vector, this is the vector, this is the point. And I'm going to create here a C# script that is going to take the origin, all right, and that's going to be of the type point3D. It's going to take the x direction, and that's going to be of the type vector3D, and it's going to take a third input that is going to be of the type vector3D as well. And then here, I'm going to output PL, which is going to be the plane. And I'm going to plug everything in here, the point, the vector, the other vector, and then inside, very similarly, in the algorithm, I'm going to say I'm going to create a plane object, PL, which is going to be a new plane, which takes another plane. I can take an origin and a normal. I can take an origin in the XYZ and the XY directions. I can take 3 points. I can take A, B, C, and D. So I think for this one, I'm going to like the origin and the two vectors. So that's going to be O, the input, capital X, the input, and capital Y, the input. And then the outputs is going to be PL uppercase. So that's the output. Is going to be equal to lowercase PL. As I do that, you can see that I'm getting a plane that is here centered on this point, correct? And that has the orientation of these two vectors. So if I change X, you can see how the plane is rotating in 3D. And if I change Y, you can see the other point, correct? All right, so we can create primitives now. And I hope that this was useful to see the simple ways of how can we create basic geometry inside of C# script components and access Rhino Command, which is the underlying geometry kernel for creation and for simple manipulation of geometry data types. What I would like to do now on the next video is to reinforce this idea and show you some more extended examples, specifically for vector algebra, where we're going to be operating and doing things with vectors. Okay? So in the next video, which is going to be an exercise video, we're going to continue with the plugin that we're building, and we're going to create a few vector algebra components, and we're going to keep looking at different things that we can do with the vector 3D structure that comes with Rhinocoma. All right? If you think we're good, you're welcome to skip to the next video where we're going to do advanced geometry scripting. Otherwise, I think the vector algebra will be super helpful. Okay? Thank you very much. If you like this video, maybe hit the button, maybe subscribe to the channel, and see you on the next video, vector algebra exercise. Bye-bye. Okay. All right. Okie dokie. So, just give me a second. I need to send an email. Okay. All right. Okie dokie. So what are we doing next? What are we doing next? Okay, the video. All right. So before that, I'm going to save this. And then in the next video, I'm going to start with the utility components and this. And I'm going to start with, so we had this file that we created, utility components. So what I'm going to do is I'm just going to copy the components that we just created, and we're going to build them into the library. Yeah, so utility components, I'm going to copy this, and I'm going to start here a tab called vector components, and we're going to create here, we have construct point. We're going to put that somewhere up here. We're going to put that somewhere up here, and we're going to give it a panel. We're going to deconstruct point, and we're going to place it in here. Okay, so that's another one. And then what else are we going to do? Then we are going to, I'm just putting in order the files that I just created. I'm going to save this as E2 vector components. Okay. So I can construct a vector. for example, and I can construct a vector from 2 points, vector from 2 points, and I can say a point here, and that's going to be A, and I can create another point that can be EV. I'm going to internalize the data so that I don't have to have stuff, blah, 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 and then I'm just going to copy and paste this. Oh wait, sorry, this should be a vector, right? Sloppy. I know, it should be a point, vector from 2 points. Exactly. There you go. Construct vector, vector from 2 points. Okay, so that's good. And then a line from 2 points. We're going to, I'm just going to use the same stuff. I'm going to use these 2 points for the line. And then I'm going to create a, I can do this here. And then I'm going to create a plane from a point and from a vector and from another vector over here. Whoop. And I am going to internalize all of this, internalize, and then just put it here. And I think that's everything we've done, right? Point that line. Oh, nope. I'm going to put this here and then point at line. The line is going to be this one, and this is going to go from 0 to 1. All right. That sounds about right. Plane. Okay, vector components. Okay. Beautiful. So this is going to be adding up to the library that we're building, the plugin, correct? The utility additions, the traction, string length, string concatenation, series, range, and then here we have construct point, the construct point, construct vector, vector 2 point plane, line, point at line. Okay. All right. So what's next now? Oh, what is next? We're going to do a few exercises where we're going to do vector algebra. Okay. And for vector algebra, I have here in my notes that we're going to unitize a vector. We're going to get the length of a vector. We're going to set the length of a vector. Maybe actually that should be, we're going to do vector addition. We're going to add 2 vectors. Vector cross product. Because of course, a plane from 3 points. And we're going to tween a vector, which is something that is not part of the standard set of Grasshopper components. And I think for these ones, what I would like to do is I would like to, I think for these ones, what I would like to do is I would like to all right, I need to go. I'll be right back. I'm going to need 5 minutes. Okay, so I'll be right back. Hold on, give me a second. I have something to deal with outside. I'll be right back. 5 minutes. 5 minutes. Can you hear me? Yes. All right, I'm back. Sorry, I have a table in my apartment that I was trying to sell on Craigslist, and they just came and pick it up. So real life, and live streams. Anyway, let me send one email that I need. Yeah, yeah, exactly. So, okay. So where were we? Ah, we were about to do vector algebra. Of course, one of my favorite topics in the world. I have sound, right? Yes. YouTube is telling me that there's no sound on this thing. Okie dokie. Yes, what was I doing? All right, so vector algebra. What are we going to do here? So what we're going to do is, did I record the introduction to the other video? I did not record the introduction to the other video, right? Oh, okay. All right. I did not record the introduction to the other video. Okay, so I need to do that. Okay, so I'm going to do that. What is the other file? This file. Oops, oopsies. Okay, so I'm going to turn everything off. Okay, so let's record the introduction then. Hi, this is Jose Luis here at Parametric Camp, and welcome to another video in this series, Advanced Development for Grasshopper, where I'm going to teach you the basics of how to script with simple geometry types. So in this video, I'm going to teach you examples of how, for example, to create your own component where you can construct a, what is going on with me? Oh, yes. Okay. Again, we're starting over again. I got really confused here. Starting over. All right. Yeah. Okay. Yeah, sorry. I'm still very distracted with the whole thing happening in my apartment. All right. So let's go again. Again. Hi, this is Jose Luis here at Parametric Camp, and welcome to another video in this series, Advanced Development in Grasshopper, where what I would like to teach you is how to script simple Grasshopper components using simple geometry types. So what we're going to build here together is, for example, a component that creates a point in three-dimensional space just by taking three numbers, and you can see that the code is going to be very simple. It's more about using and learning how to construct data types that are coming from the Rhino Common core library. All right, I'm going to teach you how to deconstruct a point into its components. I'm going to teach you how to create a line between 2 points, for example. I'm going to teach you perhaps slightly more complex topics, so how to find a point that is along a particular point on the line. We're going to also create vectors between 2 points. We're going to construct them, and we're going to create planes on a particular origin and with 2 vectors as their main orientation. Again, this is going to be very simple applications of the Rhino Command library to create geometry types. My hope here is to introduce you slowly to the topic. We will see more advanced examples further down in this series. Okay, so let's take a look at points, vectors, planes, and lines. How to create them from scratch. All right, I think it's now time to do some vector algebra, right? Okay, this one. So, I'm going to turn everything off too. I'm going to turn this off and off and off, everything off. Everything off. There you go. So then I'm going to record the introduction later. Oh, it's 12 already. It's 12 already. Do I have time for this? I think it's I'm going a little over time here. You know what? This vector is not going to take me much, but I have a headache a little bit, and I also need to sit down and to think about the examples that I'm going to do for the next video. So I think I'm going to want to take a little bit of time. So I think at this point, maybe what I'm going to do is I'm going to stop recording, because it's also been 2 hours. Probably you're also tired. I'm tired myself. So I'm going to stop recording here, and then we're going to start at 2 p.m. in the afternoon, and we're going to we're going to do some vector algebra components. We're going to do some advanced geometry, so curves, surfaces, B-reps, and that kind of stuff. And then we're going to do a few examples also about those topics, okay? In the afternoon. I need to think exactly what examples could be good for this. So yeah, I need to take a look at that. All right. So yeah. Okay. Yes, so we're going to do that. Any questions? Any comments? Anything you want to go over? Q&A? Social? It's been a lot of conversation today. Very interesting conversation in the chat today. All right. So then with that, I'm going to call it a morning, but again, we're going live this afternoon again at 2 p.m. my time, so in 2 hours from now. Okay. Thank you very much, everyone. Thank you for being there as usual, and I'll see you in a bit. Bye-bye.